Hello, my name is Juergen Jaeger from Siemens Digital Industry Software, and I'm happy to join you today and give you an overview and introduction about our Veloce proFPGA FPGA-based prototype system, which features the latest AMD VersalVP1902 FPGAs. And these big FPGAs, as you can imagine, bigger is sometimes or always, almost always better, allow now things that were previously much more difficult to do in prototyping. So let's get going. Let me take you through a few slides here. So first of all, when we look into what is FPGA-based prototyping used for today and why it's so popular, we have to keep in mind what are challenges that the industries are facing today when it comes to digital chip design, SoCs, and even IP. And more software really defines everything of what the systems are doing. And differentiation for the end product comes also more and more from the software rather than the hardware. That in return means software workloads are way more complex. You have many times multiple cores, multiple CPUs on the system, in some cases multiple operating systems, much bigger software stack, driving graphics, driving algorithms. So software workload really explodes in complexity and in size. Of course, the hardware device itself is also becoming more complex and bigger, but in the end, if you look at the hardware itself without any software running on it, just think about your smartphone, it would just be a very nice, but also very expensive and very useless paperweight. Now, to address these challenges that the industry and you as a designer are facing, you sometimes hear this term shift left, and shift left means nothing else that you want to start to run software validation and hardware software integration as early as possible, or as far left you want to start with it. And that also means that you have to have an environment and a vehicle that now allows you to run production software. Here we are mostly talking about firmware and operating system level software as early as possible and on a cycle accurate model of your non-existing chip on your non-existing hardware. Now, why is it that these challenges are really so prevalent today and there's so much attention on it? Well, as often it comes down to money. So if you look at the top chart here, that is a breakdown of the total cost of a digital ASIC chip design into the various categories. And what sticks out is that the green and the yellow bar, the green bar is software, the yellow bar is verification, are by far the biggest contributors to the development cost, to the design cost of a chip today, which may be surprising because you would think, the IP, the architecture, the physical chip design is the most expensive one. But those are all the small bars at the bottom. So software is not only dominating the contents of the SoCs today, it's also dominating the cost associated with developing it. Now, the other aspect that leads to this shift left and starting software integration and software development as early as possible is simply the cost of bug fixes. The later you fix something, the later you find an issue, the more expensive it is. And that is what the bottom chart shows you, where you can see that during functional tests and system tests, it's relatively inexpensive to fix the bugs. Once the product is released and you find an issue, it is astronomically expensive than to deal with it. Now, how does FPGA-based prototyping address those challenges and address those issues? Well, look at an FPGA-based prototype system as a vehicle that allows you to run large software workloads on a pre-silicon cycle-accurate model of your chip design and do that at many megahertz speeds. And that now allows you to run software before you commit to silicon, before you have to ship something to the customer and find all the potential issues. Now, what is a prototype system? What is an FPGA-based prototype? What does it consist of? First of all, of course, it's a piece of hardware. So it's a board, or here you see with a nice case with nice chassis around it, and our Veloce proFPGA CS system. But it's also a lot of software. So similar to what we talked earlier, what our customers are facing, what you are facing by having a very large software content, same is true for us and for our system. Again, nice piece of hardware, but we also need a software now that allows you to map your ASIC design into this prototype system and accurately perform and be able to run validation on it. And last but not least, it's also a test bench. And when we talk about test bench and FPGA-based prototype system, it is in a broader context. So a test bench here is not necessarily a traditional simulation test bench, a VHDL or Verilog test bench software piece description. But here a test bench can also be a real-life interface, a PCIe interface, USB memory stick that you connect to now the prototype system, a monitor that you connect to the prototype system. So test bench here means anything and everything that can now stimulate your design and also gets output back from your design under test. So based on that now, the key ingredients now to be able to use this FPGA-based prototype system successfully is, we discussed it a little bit already, performance, has to run fast enough to run software, accuracy, so you need a real representation of your non-existing silicon at this point, and it has to behave as a real silicon afterwards. You need productivity capabilities in it. You want to do debug on it. You want to access memories. You want to see what is going on in the design if something doesn't work, right? And you need the ability to connect both software test vendors as well as hardware test vendors, meaning sensors, cameras, interfaces, and so on to it. If you do all of that, benefits are huge. It results in a much faster time to revenue for your overall product, for the product you're selling. And in many cases, we see acceleration in schedule that are measured in months, really. And that can, of course, be can have a real business impact for you. Now, FPGAs always go through new generation FPGA vendors like Intel, Altera, AMD Xilinx. They're coming up with new FPGAs every few years. And of course, we as an FPGA-based prototyping provider want to take advantage of these newer, bigger FPGAs, and so should you, because they have significant benefits. So here's, as an example, you see what the benefits are going from the previous generation of AMD FPGA. It's called the VU19P to the current VersalVP1902. And these devices allow you to map twice the logic into it, so it's twice the gate capacity. It has, compared to the VU19P, you will see around 2 times the speed, 2 times the performance, and it has a lot of additional debug capability that now allows you to have a much higher debug throughput. And our systems are performance optimized. They provide a lot of flexibility, and we go in one of the next slides into our hardware architecture, as well as providing the lowest cost of entry, again, based on our very scalable architecture, where you can start and then increment in single FPGA increments. And that, of course, also helps you to control the cost and to only need to buy what is actually needed. So I talked about in the previous slide about the benefits you see in it's bigger and it's faster. So here are some real life examples. These are designs that our customers are already running today. So it's not some artificial, some fake information. These are actual designs. First design number one, that shows actually going from the VU440, which is the generation before VU19P, to VP1902. And the advantages are huge here. So in the VU440 FPGA system, the design ran at 10 megahertz. Here in VP1902, same design runs at over 40 megahertz, 4 times the speed up. Compared to VU19P, it's roughly 2x, depending a little bit on the design, of course, and complexity, but you can say around 2x. And now, you know, imagine what it does to your daily life or your daily work life when you're running verification, that a test finishes in 1 hour instead of 4 hours. A lot of things you can do, improve the quality, go to market faster, spend the weekend with the family and instead of in the lab. So in that case, bigger really results in a lot of productivity and performance benefits. So I mentioned earlier scalable hardware, and so our proFPGA CS system comes in 3 different configurations. First configuration is, if you will, our entry, our baby system. This baby system has a single FPGA on it. So it's a very nice, compact system. You see the dimensions, 20 by 23 by 28 centimeters. So a nice little cube, weighs about 8 kilograms. I can plug it into a regular outlet, draws something like 350 watt power, so about 1/3 of a hair dryer or a blow dryer. And the top, which is exposed now here in this picture, there's also a cover you can put over it. So once you have set everything up, you can completely close it up and walk it around, drive it around. So this is really ideal for office environments. If you want to go somewhere, show a demo for IP validation or mobile application. You have a mobile application where you need to be mobile in the car. That is a very nice system to do that. The next step up then is our quad and hexa desktop. Quad up to 4 FPGAs, hexa desktop up to 6 FPGAs. But again, you can install the appropriate number. So hexa doesn't mean there will always be 6 FPGAs in it. You have basically 6 slots that you can populate with FPGAs, and then depending on the requirement, a certain number of it. 19-inch wide, that has a 19-inch form factor, multi-system capable, multi-user capable, so you can run multiple designs concurrently, have multiple users concurrently. This is a preferred system for a lab environment, and because of the scalability, it can handle designs from small to big. And then if you want to get really big, we also have a rack-based system. These are the hexa blades, so again, up to 6 FPGAs, hexa, and it's rack mountable, standard 19-inch rack. And this is also multi-rack cable. So in this case, in this form factor, you can have up to 60 FPGAs in a single 19-inch rack. And then, of course, if you need more, you can add more to it. And this is now ideal for data center and FPGA farm application. Very important also for data center, it has front to back airflow. forced air cooling only. You don't need any specific additional cooling. You don't need a cooling in the rack itself, so it's all self-contained in the blade. Now, that's the hardware. Now we talk a little bit in the last few minutes about software. And typical tasks you go through when you map now an ASIC design into an FPGA-based prototype is that you have to do certain changes, transformations. Just think about memories. In ASIC, you can have any kind of size of the memory, any kind of control interface, and the number of ports you need on it, small and big, doesn't really matter. FPGAs are way more restricted. FPGAs have only fixed size dual port memory. So mapping now the ASIC memories into FPGAs can be a time-consuming task if you have to do it manually. Gated clocks, another example, which FPGAs don't like, which you definitely do in ASICs for power preservation reasons. And then, of course, you also want to make sure that after all this transformation changes you need to do to map a design into FPGA, it does the right thing. It's functional. And that is what our Veloce for Prototyping Software, in short, VPS software, does. It has, of course, automatic modifications of the RTL, or I would more call it transformations, so it's more appropriate to fit into FPGAs. So it does your memory inferencing, gated clock conversion. In many cases, the design, your ASIC design, your chip design will not fit into a single FPGA. Then you have to partition it into multiple FPGAs. Partitioning then also includes you have to preserve timing. You have to insert pin multiplexing because you never have enough pins on these FPGAs, on these chips to connect everything to it. So we have a partitioner that can do the job completely for you, fully automatic, but it also gives you enough or full control, and you can go all the way to manual partitioning. Most of our users start with automatic partitioning and then, with the knowledge of the design that they have, guide the partitioner to improve the results. And that then leads to the best possible performance you can get out of such an FPGA-based prototype system. Now, it's still a verification tool. That's what we're using it for. We use it for verification. That is the main purpose of it. And that means you need visibility into what is going on if something doesn't work as intended, which is expected this early on in the design cycle. And there is this traditional probe-based debugging that has always been done on FPGA, and basically means you synthesize, you compile logic analyzers, soft logic analyzers into the FPGA. So you have logic analyzer function that, as a soft logic analyzer, you map into the FPGA. That, of course, requires that before you compile, you have to define which signals you want to see, and there have to be instrumentation added to the signals you want to see. If you want to see something that you haven't specified up front, you have to go back and recompile the design. And that can, of course, be pretty time consuming. So we have created a way more usable version of this probe debugging than what the FPGA vendors are providing. So here we can specify at compile time multiple debug stations. Each of these debug stations can have thousands and thousands of signals that you specify, and then during runtime you can switch between multiple debug stations and without recompiling, and that now gives you, of course, much more flexibility in this probe debugging. Now, FPGAs, you saw it earlier, the VP1902 is a very big FPGA. Gives you some data. You can fit somewhere between, depending on your design, 50 to 60 million gates ASIC gates into a single FPGA here. And so probing everything that goes into that FPGA is often not practical. And so we have added a probeless debug capability to it that basically functions like a software simulator. No need to specify any signal at compile time, so it's all done at runtime, where you simply select which signals you want to see now, how you want to create your waveform. This kind of debug is using a different mechanism of getting this information out of the FPGA, so it uses a scan chain. And that, of course, also means it will run slower than the probe debug. Probe debug doesn't slow down the FPGA-based prototype. Probeless debug will definitely slow it down because the system now needs time to scan out the register contents. The combination of both, that is where the real power now is, because that now allows you to run at full speed on the FPGA-based prototype up to a point where something interesting is happening. So you have a trigger condition, something doesn't look right, you trigger on certain bus, can set up very complex trigger conditions. At this point, you can switch to the probeless debug. Yes, the system will run slower, but now you have visibility into everything that is in the design. You can create your waveform out of it, and once you are done past this interesting steps and you have captured enough waveforms, you can speed it up and run at full speed again. So the combination of this probe debug and probeless debug, that is where the productivity gains now really come into play. Veloce proFPGA CS is not the only product we have in the hardware-assisted verification space. It is part of our 3 system that we announced in 2024 already, starting on the left with our Veloce Stratos CS, which is a more traditional emulation system that can go to very, very high capacity. A lot of use modes that you have on it for DFT, power analysis, coverage. So it's really, if you will, a software simulator on steroids. There's a companion to it, which is called Veloce Primo CS, which is based on the same VP1902 FPGA as Veloce proFPGA CS. This now allows you to move a design that is up and running on Strato on the emulator very quickly to an FPGA platform, get an additional acceleration, or get a lower price point of the system, and therefore a very productive environment. And then, of course, we discussed proFPGA CS at length in the previous slide. That is our high-speed, high-performance FPGA-based prototype system. Combination of it, it depends on what your requirements are. In the end, also what the size of your wallet is, if you need all 3, if you need only one of those 3, if you need a combination of the one or the other. So we have complete flexibility also in adapting to your needs. And so to sum it up, FPGA-based prototyping is an essential tool for any SoC and digital chip design and IP these days. Choosing the right prototyping solution is critical. I mean, there are many choices you can make. You can also choose to build your own boards with your FPGAs. And in the end, no matter what you choose, make sure you consider both the hardware aspect of it, so you need the hardware to run it on, as well as the software. In this case, both the implementation software. How can I map my ASIC design into a bunch of FPGA, as well as the debug aspects of it? How do I now gain visibility? How do I have access to the memories? Can I look into what my caches are doing? So look at the prototype system, not just as a board with FPGAs on it, but as a whole system, as a whole solution to help you do your verification job better and faster. And with that, I want to thank you and open it up for questions you might have.